Gautam Menon is a professor of physics and biology at Ashoka University, Sonipat. He was previously at the Institute of Mathematical Sciences, Chennai, where he worked in the theoretical physics and computational biology and was the founding dean of the computational biology group. He served as a dean of research at Ashoka and was an adjunct professor at AFR Mumbai and a visiting professor at the Mechanobiology Institute, National Institute of Singapore. His honors include the DST Swarna Jayanti Fellowship, DAE SRC Outstanding Research Investigator, and APS Outstanding Referee, and he is a Shastri Fellow. He is an elected Fellow of the National Academy of Sciences, India. He also serves as a commissioner on the Lancet Commission on Epidemiological Modeling for Pandemics. He is a co-author of the Lancet Commission on a Citizen-Centered Health System for India and is a member of the WHO Technical Advisory Groups on Ethics in Health and Climate Change Policy. Over to you, Professor.
Thank you to the CNI for this kind invitation to speak here about stuff that's close to my heart. The talk is about how models for disease spread help us more broadly think about what is good policy. And that's really where we should be thinking about as people who are interested in the application of what we do to real life situations. And we can start by just saying, what is a disease model in the first place? Let me just get rid of that. Can't find my cursor anywhere. Can you help me? We did that earlier and now we can hide them again. Yeah, sorry about that. So let me describe what these problems are and what the questions are here. And let me start by defining what is a disease model in the first place. And the simplest models for disease spread are what are called compartmental models. And among compartmental models, the SIR model is definitely among the simplest. So the idea is if I have a population of people, I can put them into different boxes or compartments. One is a susceptible compartment, that is where you have not contracted the disease. The second is the infected compartment, the one here, where you are both infected by the disease and potentially able to infect other people. And finally, there's a recovered compartment, or R, after which you cannot be infected again. You assume that after contracting the infection, what's happened to you is that you've now become permanently immune to the disease again, to further infection. The way one takes a picture like this of compartments and people transiting between compartments is to say that, look, you have a susceptible, during a process of infection becoming an infected, and from there going to a recovered compartment. You can write these down in terms of a set of coupled ODEs, nonlinear ODEs. And here are the equations that describe what those ODEs are. This says the numbers of susceptible per unit time, or the rate of change of the numbers susceptible is proportional to the interactions of susceptible and infected. So that's S times I, and there is a rate that governs that. And you can figure out the right normalizations here. And of course, if you add these numbers up, ds by dt plus di by dt plus dr by dt, you should get 0, because the total number is assumed not to change. And as I said, this is how one thinks of the simplest types of disease model. They're just coupled ODEs that describe numbers in each compartment, and deciding which are the compartments that are important that you want to model is one part of what goes into thinking about these models. Because there are many models, and with all of varying complexity. And here are two very complex models, or somewhat more complex models. This is a model that was used here to think of COVID-19, and this has a susceptible and exposed compartment and a whole bunch of different infected compartments, asymptotically infected, pre-symptomatic here, symptomatic, mildly infected, recovered, etc., here. So all of these in this little dashed box here are infectious potentially, and they can act on the susceptible again and make them exposed. And this is an even more complicated model where you have unvaccinated, single shot vaccine, double shot vaccine over here. where you might want to ask what's the right scheduling of the vaccine, who should you be vaccinating, should you vaccinate older to younger people or go the other way around, should you vaccinate just people in working age, etc., and ask for each of these choices that you might make, all of which are policy choices, which is the best overall in terms of some metric that you have. So this is very classic work. I mean, the whole compartmental model business began roughly 105, 110 years ago with classic papers in the 1920s, the 1930s, etc. So that's a long while ago. And these ideas have been placed since then. In fact, they even go back further, a further century or two to Bernoulli and other people who worked on this. But one can ask, where does one go from here? One has now accumulated a lot of knowledge from what happened during COVID-19, where large fractions of the world were really interested in this question of what's going to happen next week, 2 weeks from now, 1 month from now, etc. So what happens, what is the new generation of disease models? What should they be concerned with? The other question is, I mean, modeling is fine as a mathematical exercise, but if you want it to be useful to the real world, you have to ask, how do your models and your model predictions, how do they translate into policy? What are the sort of interventions that you might make, and how do you assess which intervention might work? How do you assess which combinations of interventions, for example, vaccination, quarantining, etc., etc., etc.? How do they add up together? There are far more subtler questions here when it comes to what are called the social, economic, and other determinants of disease. One simple example is a recent study called the Ration study, where they looked at just food supplementation or diet supplementation of TB patients. Now, that's not a medicine, that's not a drug. It's just looking at a bunch of patients, and you take them, you take their families, and you provide them an extra set of rations to supplement their diet. And they found this had a huge impact on controlling, reducing mortality, as well as overall reducing the progression of the disease in a significant way. That has to do with social and economic conditions and the targeting of appropriate interventions at that level. And that's why these are generically wrapped into something called the social, economic, etc., determinants of health. And of course, if you're talking about individuals, you want to ask about what does the genetic background do, what does immune response do, etc. And to answer all of these questions, you need to be more granular and more specific as possible. This idea of taking everybody and putting them into a susceptible box or infected box won't work anymore if you want to ask these more granular questions. So we started with just simple compartments S, I, and R. We can structure these compartments. For example, we can take a susceptible compartment and divide them into subcompartments which are age 0 to 10, 10 to 20, 20 to 30, etc., etc. Because you know that a disease like COVID affects the elderly much more than it does young people. So in that sense, breaking it up into old and young at a first approximation, or even choosing some division that is sensible when thinking about the disease, is a good way to do it. And that's adding structure to the compartments, but otherwise leaving the idea of the compartmental model the same. Then you could work with networks. You could argue that the way disease propagates from person to person is that you're in a spatial network with people, and whenever you're in the same spatial location, if you are infected and the other person is susceptible, there is some chance that you will transfer that infection. So that's when you can talk about agent networks here. And of course, the last step here might be to talk about each individual separately with all of their complexities and therefore all of these different colors here. And going from here to here is just adding a lot of granularity to your description. So agent-based, much of the talk will be about agent-based models. They're also called individual-based models. You can put in movements, you can put in geography, environment, variation, etc. And they all build on networks of interaction. So in a sense, you can also think about agent-based models as very complicated networks that are time-dependent and structured in various ways. But you could just think about agents separately. And here's a picture that is useful to keep in mind. Think of people here. Each of this is a person. People have homes, they have workplaces, they transit between homes and workplaces. Some of these workplaces could be schools, they're marked here. They have places that are not workplaces and not schools. For example, in the weekends, they might congregate in some common area, etc. But this is the way you'd like to think about it. You have these different locations, people moving, some schedules that these people have, and you're now modeling every individual on their own as they are. You're modeling families, family structures, and ways of moving from one to the other. So I just want to start with the simpler idea of networks of interaction. And this is a paper that we wrote some years ago with Sandeep Krishna, also from Bangalore. And here's the idea. So here's where I want to introduce one particular model for policy. And that's, if you remember, sort of go back 3 years or 4 years ago, remember that there were two COVID-19 tests. You could either do a high sensitivity RT-PCR test, or you could do a relatively low to intermediate sensitivity rapid antigen test. And the question that governments, state governments all over the country were trying to face was, what is the right mix of these that we should be using? If you know that the rapid antigen test is not such a good test, should you be using it at all? Maybe you should be testing everyone with a high sensitivity RT-PCR test. That would be then you guarantee that your answer is 90% or 95% likely to be the right one. However, the RT-PCR test is a more expensive test. You don't want to blow your entire health budget on an expensive test when you could do the same job with a cheaper test. So that's a question. How much should you test, first of all? Should you be testing at 1% of your infected population, 5%, 10%, etc.? What's the optimal mix of RT-PCR to the rapid antigen test or the RATs? Should it be completely skewed towards the RT-PCR? Could you accommodate some amount of RAT inside? What's the right mix to take? What does this depend upon? And as the cost difference between these tests varies, how should the mix change? There's one answer that might make sense when the RT-PCR is much more expensive than the rapid antigen test, and there's another that might make sense if it's just about 1.5 times more the cost. So again here, one sort of imagines that there are homes, hospitals, workplaces, etc., and then one can put in rules that are reasonable. People move between homes and work locations. Some people may work in hospitals. That's possible. If a person tests positive, they're isolated and their homes are quarantined, and you don't allow motion for a certain quarantine period. If a person isn't tested or tests negative, they can continue to go to work. So there you can accommodate the fact that not every test is necessarily a perfect test. And then you have people going from workplaces here, back and forth, etc. These are the rules that you can think of that in a sense reproduce what you think society will actually be doing, will actually be up to. You can take this and make this a network-like model. The nodes here are locations. Individuals are links between a home and a work location. And you can imagine, you can investigate how disease might spread upon this particular network. And over here, this is the infected curve here. It goes up like that, comes down. This is a fraction of the population. So by this time here, about 15% of the population has been infected, and then you can come down again. This is the peak of that. The numbers are susceptible is 100% are susceptible or 99.99 is susceptible. It comes down and saturates here, and these are the numbers of recovered inside there. But then you can do many things. You can change testing rates. So this is the fraction of the rapid antigen test and the sensitivity of the rapid antigen test. Right over here, you're at very sensitive tests, and at this point you have all RATs. Then over here you have all PCRs at this. And you can, between here, you can say what is the total fraction infected at the end of the epidemic. You can change quarantine procedures. You can quarantine when, I think when you have DTR about 0.1%, 0.1, the daily testing rates are at different levels. You can decide when to quarantine, vary testing rates, look at NPIs, look at masking, etc. And then finally figure out in the space of possibilities, what's the best policy decision that you can actually take. And it turns out that you can actually compensate for less sensitive tests by increasing testing rates. That provided you test more, you can outweigh the fact that the tests that you are using, the rapid antigen tests, are just not as good as the RT-PCR tests. This had been inferred earlier in your work, but this particular result, when we came across it, did attract some amount of attention. You could also calculate economic trade-offs, which, given the costs of the test, which is a better test to take in terms of overall cost reduction as well. Of course, this was a moving target, because you remember what happened was that state governments negotiated very stringently with suppliers. And so they brought the cost of the RT-PCR test from 4,500 rupees to something like 1,500, 1,000 rupees, where it was competitive with the rapid antigen tests. The trade-off was that manufacturers potentially began to skimp on the quality of the reagents that they used in the tests. So that was something that was an unanticipated, or perhaps anticipated offshoot. But you can see that even the decision that you take is in a sense a function of time. You have to figure out where in that space you're moving around and take the right decision. Overall. So typically at the peak of our testing, we were testing about 0.1%, 0.05 to 0.1% at the absolute peak of our testing in India. But you can look at a whole range of testing rates. So if you increase the testing rate by a factor of about 2 or 3, you can compensate for the fact that you're using a less sensitive test versus that. So that's a trade-off that we were trying to emphasize in this particular case.
So symptomatic people or
You are testing everybody. Some at random, some fraction of them will be infected, some fraction of them will not be. Sorry, I should repeat the question that you're asking. Yeah, so the questions were about when the tests were done, who were the tests done on, And that was one question that was asked, to which I replied most. You are basically testing at random people. So the question was, who were you testing and what was the coverage that you were doing? You were testing at random in the population for people. Once you identified, as I remember, once you identified someone who had tested, you tested their family as well and you quarantined them and you moved them out. There were limits on the number of tests that you could use in a particular day. So it was set at 0.1%, 0.05%, 0.2%, etc. And that reflected the normal constraints that the health system had to deal with at that time. Is that a question? No, so the question is 0.1% enough? And the answer is that it's clearly not enough because the numbers are increasing. But the question is, what is the capacity of your health system to test? In India, the best that we could do was about 0.1% at the absolute peak. Typically, we were testing far less than that. And then the question was that, with that constraint, if you took those sorts of constraints and applied them to the disease here, this particular question, what would you do? What would you be able to do? It's also a question of when you test. Okay, are you testing early on in the epidemic? Are you testing a little later? But all of these we could actually check in these simulations and ask at different times, at different at different price points for these different tests, what would be the optimal strategy? And that really is what a policymaker would like to know.
One other issue related to RT-PCR tests taking maybe a day or 2 days.
Yes. We did that, we incorporated. So again, to repeat that question, the question was that the RT-PCR test, there is a delay in the results coming, could be 24 to 48 hours. In some cases, it was much larger. It was 4 to 5 days during the peak of the Delta wave in Delhi and other places. So is that incorporated here? Yes, it is. And those delays turn out to be very bad in the sense of being, you lose your ability to control the epidemic completely if you allow for such large delays. So we could also look at that in this particular calculation. So again, there was a lot of interest in this result when it appeared at that time. The other question that we were asked in the WHO, the Strategic Advisory Group on Emergencies, which was the policy group at the worldwide level that was trying to decide what is good policy, was should schools be opened or not? Those of you, if you go back 4 years or 5 years to when all of this started, you will remember that this was a very important question also for parents of little children. And you can see what the trade-offs are. No parent wants to see their child fall ill, potentially seriously ill. But on the other hand, society as a whole does not benefit if young people are out of school for a period of 1.5 years to 2 years. What do you weigh in this particular case? What is good policy in this particular case? And how does one think about it? You can work with a slight modification of that where you include schools as well, schools, workplaces, etc. You send children to school and then you can ask, given that you know that children will generically have much milder cases of COVID, in fact they may not even notice that they have COVID, what would your policy be? So now you have to put in the age stratification, the impact of COVID, the likelihood that you will have a serious case if you are between the ages of 0 to 10 or 10 to 20, etc., etc. And here it turns out that actually if you put the numbers in, you could have actually sent children back to school fairly early on. Because the impact on children and on children, serious cases in children was actually very small. The more serious impact was on the people at home. That you could in fact get over by saying, take all families of school-going children and vaccinate on priority those families, especially the elderly in those families. This would automatically take care of one route in which the child goes, gets infected, child shows no symptoms at all, comes back home, but then infects the grandmother and the grandfather who potentially could fall much more seriously ill. So this again, the sort of policy question here was that you could have actually opened school. This is a political decision. It's not as though there was much careful attention paid to what the models were saying, what should this. Finally, even the government of Karnataka in this particular case said that, look, we cannot go against these parents who are telling us that they don't want schools to open. But again, that's where the complexities of society come in, that the people who want children to stay at home and not go to school are typically more well off. And people, if you look across the whole socioeconomic strata, people who need their children to go to school so that they can themselves go and work outside, that's by far the larger part of the population, but their voices were not heard in this particular decision. That again points to the complexities of decision making not so much as the complexity of the answers that come out of the model. So we wrote an article saying precisely this. And again, I sort of want to make the point that if you want to influence policy in any way, it's also good to be able to communicate what you do at a technical scientific level to places, to people who will read and find out what it is that you are saying. And so that's another thing that we thought we had to do at this point, which is help to communicate the results of models and modeling and where they were actually leading to people. And later, sort of my co-authors on this and I went back and we thought that this was one point we should have made a little louder and a little more strongly. We did talk to various state governments about this, but we did not make the public case as strongly as we should have. And I think we're still seeing, in a sense, the consequences of that even now. And we probably will see it for the next decade or so. This is 2021 that we wrote this article. Okay, so now I want to move from the network model that I showed you in those examples to something called BharatSim. And this is the paper, it came out in PLOS Compile in 2024. I want to tell you a little bit about the history of BharatSim and what it actually means. So the BharatSim program actually began, as all of these things begin, when someone funds you to do something that you can't do otherwise. And there were discussions with the Gates Foundation, which started, because I have all of the emails, I can go back and check exactly when it started was on March 30th, 2020. The Gates Foundation was interested in models for COVID-19, but they also wanted to assess economic decision making. So they said, is there a model that will allow us to look both at what the disease impacts are, as well as what the economic costs are in any way? So they evaluated the proposal, they approved it very quickly. So by June 1, so March 30th to June 1st, which is kind of historical in terms of short grant approval timelines, and they extended this further. So I'll tell you a little bit about what this is, but I'll tell you how it came together. We collaborated with a company called ThoughtWorks, an engineering consultancy company which works in writing technical software, and with a colleague of mine in computer science called Debayan Gupta, who was interested in one part of this called the synthetic population. And ThoughtWorks did much of the coding in a professional sense, and we discussed with them what we wanted and kept a very careful eye on what they did. So we worked very hard, as I think all of us did at that time. I remember Rajesh's group also doing lots of agent-based stuff at this point. All of us were very deeply involved in that. We met very regularly with ThoughtWorks, with the Gates Foundation, and much of the discussion with the Gates Foundation was actually very technical and very useful. So they were funders who, unlike DBT, etc., would actually sit and talk to you and discuss technical issues for hours about what it is that they wanted, what it is that you could do. So that was a very pleasant experience working with them. And my student who led this really worked tirelessly on this. As at that time, I met all the people I wrote this paper with only something like almost a year after that. We started in June 2020. By March 2021 was the first time we actually physically met, even though we'd been talking online for something like 9-10 months before that. And the Gates Foundation people, again, I had spoken to them for about a year and a half, but to physically meet during the time that we were all emerging from the pandemic took even more time there. So what BharatSim is that it's an agent-based model of disease spread. And it can simulate up to about 50 million individuals, but most useful simulations, as you will see, are actually smaller. So this is the BharatSim website, which you can just type into your browser and locate. And from here you can download the software, you can look at examples, publications, etc., etc. You can work with BharatSim at the level of a community. For example, if you want to discuss school openings, you would look at schools and the community that fed into those schools. You could look at a district. If you want to do a localized lockdown, you might want to lock down one particular district. You could look at a state. And by the time you get to a country, you can look at questions of migration, which again was a major issue there with people going back during the lockdown to long distances and presumably carrying the infection with them. But with a really large-scale simulation, you can begin to answer some of these questions. And we certainly can't do this, but we could do up to the size of a small state with the sort of numbers that we had. Although we never really did that. We did, at the most, we did one large city, one mega city inside India. The code was written in Scala, designed for both parallel and serial use, and it had three parts: a simulation engine, a synthetic population, and a visualization engine. I'll tell you what each of these things are. The simulation engine is the basic part of it. It's a grand sort of engine that thrums behind all of this. So we have agents, we have home locations, and we have work locations. That's division that we maintain. We could redefine work locations in various ways to turn on only in the weekends so that they're not work, but they might be markets, they might be public areas where you actually went to. And then you have relationships. This person is housed by this home, is employed by this workspace, etc., etc. And you can house multiple persons who work in other locations. You can put that complexity inside. Yeah. There are schedules that these agents have. Typically, you might want to midnight to 9 a.m. is home, 9 a.m. to 5 p.m. is work, 5 p.m. to 6 p.m. is market, 6 p.m. to night is home, etc. And students have schedules that involve going to school and coming back. So each agent has a specific schedule for that particular agent. It has a place to go to and a place to come back, and this can change over the days. People over the age of 18 are called employees. Under the age of 18, they're called students. And so there is a class. There's a little more structure. Some of these pictures I just showed you, the schedules here. You can imagine putting all of this together. So you have workplaces, homes, individuals transiting between all of these things, and potentially infecting. A person who's infected can infect someone else if they're in close proximity with another. What's core to all of this is something called the synthetic population. Now you might say that you have these agents and they stay at homes, etc. But tell me a little more about them. What structure can you add on top of this? And the synthetic population is obtained through a fairly complicated means. You take census data, you take IHDS, the Indian Human Development Survey data, you take microdata reflecting family structure, and create age, sex, and household size distributions to get some sort of base population with household data. So you've now put people of the right ages into households, and the structures of those households, the structures of the ages of people there, etc., are consistent with what's known from the census and from other surveys that have been done in India. Now you can take this and put the space on it. So you take gridded population of the world densities or some other source of densities here, construct polygons for them, assign geolocations, take all of this information that you had here from the microdata, and now you have people located in physical space, these agents in particular parts of the city that you can actually put here. So you have a base population with location data there. You can then take more information here. So this is the lower thing here. You can add this. And finally, when you take the IHDS and you use it using a adversarial network here, coupling it with things like the National Sample Survey and other types of survey that give you employment data, demographic data, comorbidities, etc., you can get what begins to look like a proper population. In the sense, I can pick one person out of there and have multiple attributes defined for that particular person that is broadly statistically consistent with what is known through multiple surveys. So I'll just give you an example of what this looks like. This is what a typical, it's a line list, it's a large line list. This is the unique agent ID. This is female, male, male, etc. The age is 76, your height is 147.37, weight is close to 50 kg, construction, etc., 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 etc. Seems a somewhat old construction worker. There are these slight, problems with this data. Overall, it's okay, but some of those problems come from the base data themselves. It's not as though these surveys are themselves particularly exact in many ways. So this is for the first several columns. Some are students, some works, the agricultural labor, some are homebound, etc. You can put these details in. Now you can take the synthetic data that you have made using these adversarial networks, using all of these statistical techniques to aggregate them and compare them to this age distribution. So this is synthetic data and survey data, and you can see how it does here. You can look at the height, the distribution of height, distribution of weights, the comparisons between these surveys and what is done with this method here. You can look at the fraction of children, this age between this. These sort of peaks here are because people tend to round off years to the nearest 5. So 4 will become a 5, 9 will become a 10. So that round off is here, and it's also there in the data because we draw it from these sources here. You can look at the children, heights, etc., all of this, and it doesn't do too bad. It's not outrageously wrong. It's not perfect, but I would argue that the problems with this also reflect the fact that the original survey data is not the perfect data that you might actually want. The better you have a survey data, the better the job that you can do with this. Okay, so now you have this information. You can now do things with it. And one thing that we wanted to do, that we started off doing, was to look at models for COVID-19. So I showed you this complicated diagram here earlier as a model for the different types of states or compartments that you would have in COVID. But now you can do cleverer things in the sense that you can be a little more realistic in terms of the distribution of times that you spend in each of these compartments. The dirty secret of compartmental models is that you spend an exponential amount of time in each compartment. When the time is exponentially distributed, which means that the largest fraction of people will leave that in the microsecond after they've actually entered that compartment. So this is because these models are very easy to compute with, people use them. But this is obviously not realistic, and you can, with agents, you can be much more realistic in the way that you actually assign the time that you spend in these compartments here. So, among the other things, the referees asked us, all right, suppose you had access to Pune data, whichever city you're studying, only in the initial part, can you use this? Suppose you had data up till here or here or here. Can you use this to predict what might happen, where the first peak might actually come? So for this, we had measurements of what the reproductive ratio was over here in the early part, the first wave of COVID. This is between about January 30th and the first 4 or 5 months after that. You can take this, convert this in a complicated way to the numbers that are represented in the simulations and compare that. So this is the predictions of the simulations, and these dots here are actually the data for the number of cases. So this is a calculation for Pune, so a population of about between 3 million and 4 million people here in Pune city. And there are other examples that we've actually, but you can see that it does this reasonably well. And actually, as it turns out, it goes back up here again. But that's also because the virus itself was changing. The virus that came in January 30th of 2020, the original Wuhan strain just didn't last very long. It lasted barely a couple of months and then was taken over by much more transmissible strains after that. Other things that you can do is you can ask exactly that question. What happens about if there's a new strain that turns up here? So here's an example calculated in millions in this case, where you have 100% reinfection from a second variant that comes in after this one has petered out here. And so that's over a period of about 200 days. And you can tune that in various ways. Suppose you had 100% reinfection or 90% per reinfected or 80% or 70%, et cetera, et cetera. You can see what these peaks would actually look like. So this is saying if there was some protection from a prior infection, what would that mean for the number of cases at a later point? You can also say that if you have a vaccine that you administer here or here or here or here or here, how does that second peak change? So now you're in a position to evaluate different types of interventions that you can make. You can put in vaccination. You can choose to time the vaccinations when you want. Put it before the peak, after the peak, before this, etc., etc. And couple that with what you know about the biology, the chances of getting reinfected here. And ask, to what extent can you fine-tune the policies that you're going to put in place so that something happens that you want. So my own interests, so let me come to the more specific and interesting questions here. So my own interests are broadly now soil transmitted helminth diseases. These are hookworms and which affect a large number of people who work in agricultural labor in parts of the country. This is the one, these two examples are the ones that I want to describe a little bit in the time that I have left. A potential H5N1 pandemic and mpox spread. These are two very different problems, but they're both important problems in thinking about public health. We're interested broadly, apart from typhoid, in health, climate change, environment relationships, and also in what I call social determinants. And I'll come back to that a little bit towards the end. So the outbreak of H5N1 in humans is my first example. And if you were to ask a public health, yeah, go ahead. Okay, so the questions were how accurate do the models have to be, and what's the nature of the models that makes it, palatable to the politician? I guess that's the question. How should you construct? Should you go like complex models or simple models, or what should? Yeah. So the examples that I want to use here are of things that have not happened but could happen. So both these examples here are examples of that form. They're believed to be important public health threats of the next year or 2 years or 3 years or 5 years or 10 years. But they're intended to ask, how can we prepare now, given an understanding of the different scenarios that might happen, for better making policy later. So they're not intended to be now casting scenarios, which is that right now you're in the middle of it, what will happen in the next week or 10 days. We can do that. And again, you can use whichever models you have the most faith in. Usually the problem is figuring out two things. One is figuring out what parameters enter the model. That's a hard thing to do, and that you have to be in a constant dialogue with epidemiologists who look at data, look at numbers and so on. And the second is the much harder thing, that is people change behavior. If I know that there is a pandemic, I stay at home and I wear a mask. Now that's not there in the model, because that is extremely hard to calibrate. To what extent do people take this seriously? I mean, you may have friends who say, look, this is all nonsense, I'm perfectly okay, I lift weights, etc. Nothing's going to happen to me, and they go out. And you have friends who say that, look, I'm going to be very conservative, I have parents to take care of, I'm going to wear a mask, I'm going to stay at home. So how exactly human behavior interacts with these decisions is much harder to model. And that's the second problem. One is a problem of numbers, and the second is this. So it's said about disease modeling that, ideally the disease modeler would like the model not to work, because if it really was as bad as they predicted it would be in the absence of people changing their behavior, etc., that would be a worst case scenario. And in a sense, a good model should never work, because a good model will predict things that will be preempted by decisions that are made by public people and by behavior changes. It's a bit counterintuitive to think of that, but that's actually true.
So are there ways to prioritize which properties or rules need to be put into models? Have people thought about?
So what are the rules of good modeling? So that's something that we have been working on recently in this part of this Lancet Commission on the modeling of epidemiological diseases. But what is good reporting of models? What is good standardization of models? What is the taxonomy of models that people can work with? And one very important part of that is that models are required to be fit for purpose. You don't need very general models. They must be fit to answering the specific question that you're asking. And there are other things around that. You need a close relationship with policymakers to be set in place in what we call in peacetime, that is before things actually happen. So there are a whole bunch of observations that we make, suggestions that we make for reporting, etc., that will hopefully in the next pandemic make a difference. But they have not been done in any systematic way until now.
I may not be able to phrase it very, very well, but at least my question. Let's see if I. So basically, the event such as infected is one discrete event for you. And in your BharatSim framework, you have discretized a lot of the stuff that happens in real life compared to the classic SIR models. There, time apart between individuals are also dominated and now, and then you have also very fine time compartments like scheduling between 9 to 5 and so on. How do you? I understood the spatial and the community structure part, but I didn't quite get how do you go about getting the temporal sequence right? Because if you fine tune it too much, then it's not really discrete events. Doesn't it make both the modeling and simulations incredibly challenging?
So so the question is, how do you choose your time interval between updates, etc., to more accurately represent reality? That is a modeler's choice. So right now we can choose in some of these simulations, it's a 4-hour, given that you have a 12-hour at home, 12-hour outside, we choose a 4 to 6-hour gap in the simulation that we make. And in that, if you're infected in that gap, then you're infected after that. So that, in a sense, is a minimal level of discretization that you have in this particular model. However, it also depends upon the disease, and that's in my second example, which is a sexually transmitted disease where contacts happen at the intervals of about a week or 2 weeks. So then you don't need to worry about gridding at that very, very fine level, because it doesn't make sense. There are no contacts to which you can transfer it beyond. But it is a modeler's choice how discrete you want to actually make it. There is no universal answer to that question.
But you also, as a modeler, you also have to deal with being able to not over, because at the end of the day, more fine I get, more wrong I will get about the details also, right? So that's also
I wouldn't say. I think the more fine you get, the more computationally heavy the calculation gets. But it's not otherwise. It's not a worse calculation the more finer it is, because you scale your rates in such a way that it's the same effective rate whether your time interval is small or your time interval is large.
you're saying only the update discretization, right? Update time changes, but
The bare rates remain the same, but if you choose a smaller interval, the probabilities of becoming infected in that become correspondingly smaller, keeping the overall rates the same. Okay, so let me so if you were to ask any epidemiologists what they think is the biggest threat to public health from a new epidemic, the answer may surprise you. It's actually this thing. It's actually bird flu, and a particular variety of bird flu called H5N1. And this falls in the general class of highly pathogenic avian influenza. And H5N1 is the best known example. And this is something that circulates in birds and does not normally infect human beings, except on the rare times when it actually does. So this is a subtype of influenza A, mainly affecting poultry and wild birds. It's highly infectious, and it can basically kill every bird in your flock within 4 days or 5 days, etc. It spreads very quickly in overcrowded poultry farms. It's significant outbreaks and associated fatalities, almost 100% fatal. Interestingly, it's not just in birds. So here's a marine mammal which has seen large number of die-offs. So this is off the coast of North America and South America. These are seals, which also have been infected by the same bird flu, except they're not birds, they're mammals. So it already indicates that one significant barrier between species, diseases moving between species, has actually been breached. So here's a typical headline that you might see: could bird flu spark the next pandemic, and are we prepared if it does? So that's why it's important to think about this, and we were thinking about this as a question of, in what sense are we able to prepare better for something that hasn't happened, if we can understand the rules by which it might happen and what we could do to actually intervene. So the question we used was, we used BharatSim to answer the following questions. So given a history of initial cases in humans following an outbreak in birds, how fast can the disease spread? And how can you infer other properties? Typically, you'll have a small number of cases here, 2 cases today, 3 tomorrow, 1 nothing day after, etc. Can, from this very fragmented initial information, can you go back and infer the properties of the disease? The secondary attack rate, the serial interval, etc., etc. So to do this, we used a model farm in a place, and we used a synthetic population from a place called Namakkal in Tamil Nadu, which is home to a large number of poultry farms, etc. And we had a farm here, a central farm here. We had a bunch of people who worked, homes around it, and some people in these homes worked on the farms and could potentially be infected by that. So this has 2 steps of infection. First of all, birds must be able to infect other birds. That's one block. Then it must move into humans. That's another block. Then it must efficiently transfer between humans, and that's a third block. So all of these one can put in and sort of examine the space of possibilities and ask what happens in that case. So the birds is susceptible, infected, and dead, because as I said, this is 100% fatal in birds. And here is the human beings, which is an SEIR model. And the number of infected birds contributes what's called a force of infection that acts to take a susceptible human being and make them exposed and later infected. You can look at all the literature that exists on this, that's available, and try and from that look at the duration of exposed, the duration, the probability of all of these things. You can fit them to various functions with very fragmentary data, because there have been relatively few cases. We've seen infections in humans. We know that in humans the fatality rate is between 30 to 40%. Remember that the fatality rate for COVID is somewhere between 0.1% to 0.2%, let's say. This is 30 to 40%. So the scale is just huge if it actually managed to spread efficiently in human beings. As I said, this is the sort of data that you might look at here. This is a primary case. So on day 10, you might see one primary case here. You might see another case on day 12. Then you can see a family member, a secondary case here, a secondary case here, secondary case here, secondary case, another primary case. This is the very, very fragmented data that you might get in an actual, because you're doing an actual granular simulation of individual people getting infected. You can figure out the true noise that exists behind this data. You can take this and say, all right, I'm going to take all of this and I'm going to cull the birds, because that's the only real solution to a bird flu. You don't want it to spread to other farms. So you take the birds, you kill them all together, you burn them in some large pit, etc. But you can control when you do that. Do you do that early on in day 10? Do you do it after the peak on day 20? Or do you not cull at all? And then you can ask, what are the consequences of this based on the bird-human, in the possibility of an infection transferring from bird to human. And this is the fraction of runs which ends in no infection, in 1 infection, 2 infections, etc. And you can see what these actually look like. The earlier you cull, the less chance there is of having, the more chance there is of having 100% of no infections at all, and barely between 1 and 2 primary infections. The later you do it, the more chances there are of having primary infections, which can then later spread. This again, this fact that you didn't have much time to make the decision was again sort of much discussed at that particular time. And again, this paper got a lot of attention when it was actually written and came out. Mainly because we said that you actually don't have much time. If it turns out to transmit efficiently between human beings, if you do not catch it at the point where your first primary set of infections have happened, once you let it leak out, because you infect someone at home, that someone goes to school or that someone goes to workplace, and then the potential of that spread becomes just exponentially much larger. So there is a very short window you have in which to actually respond, and ideally you should cull as early as possible before the peak in that infection actually happens. In birds it's very easy, because they as soon as they get it, they start walking, staggering around. Within a day or two, they're dead. So that's not a problem. The problems are, as I said, often more social. Farmers might not want to say that their birds have been infected, because that it has reputational consequences. They will lose all their birds immediately, and potentially that will actually spread to other farms there. So concealment is often an issue, not so much the fact that you can't detect it, which is why you need very good surveillance at this level. Yeah, so we're talking about the mutated strain that can affect humans. We're saying, let's assume that it can affect and transmit efficiently between humans. You say that after that first jump has happened to humans, what you can control is two things. One is the rate at which it moves to humans, and the rate at which it moves between humans. So you vary both of that, and then you see. So you're already assuming that you have something that can transmit between humans and infects humans. That's there. But then you can ask, how effective it is at moving between humans, and how effective it is in jumping to humans in the first place.
So, as you said, like your model is telling that cull everyone at time 0. So then,
as early as possible. I mean, time 0 is probably too, but the advantage so that would be the recommendation, which is a policy recommendation, saying that surveillance should be of such quality that you can detect bird flu in birds early enough, and you can arrange to quarantine those who work and the family members of those who work in those farms if you suspect that there is some chance that someone may have contracted it. As I said, there's a bunch of bottlenecks. One is that once a bird flu is common in birds, we don't have to worry about that. But the H5N1 going from birds to humans, it has to surmount a barrier. Between humans and humans, it has to surmount another barrier. So both of these must come into place. So if you're absolutely sure that that second has happened, then you should really be really hype up surveillance so that you catch it as soon as possible. Okay, the second example here is example of outbreak of mpox in humans. And those of you who've been reading might have sort of read about the last few years, typically over the last 6 years, there have been these cases of mpox, typically in western parts of Africa. And Sierra Leone, explosive mpox outbreak in Sierra Leone, overwhelmed health systems. And over here it says this person who was quoted here says, I think this could very well become a much larger and more global problem. Mpox is a sexually transmitted disease. It goes through typically men who have sex with men. But what's slightly worrying about all of this is, first of all, there's a large number of women getting infected, large number of children getting infected, and it's not clear how that was actually transferred to them. So the worry here is that it has escaped this network. It's able to escape this network of men who have sex with men. And then how we think about it becomes very different. It's not, India is not unused to this. It's largely transmitted by tourism network, but it seems to be possible to transmit outside this network, to close contacts, to family members, maybe just sharing the same towel, because it's typically associated with the transfer of fluids from one to the other. And that the whole complexion on this, that is very different. So what we did here was to model mpox through two channels. One is purely sexual, contact with a subnetwork of men having sex with men, MSM. But this is embedded in a larger network of households and people who work. So, for example, a picture like this. Here's a network that this is data. It's hard to get data for these things because there are many privacy issues associated with this. So you have to look at these pictures that have, these network pictures that people have done of data, and from this extract network information and reconstruct sexual networks appropriate. So this is from 3 cities of Karnataka, Gautam being one of them. This is a network picture of network of men who have sex with men here. But what we want to do is a little more complicated. So here, this is a sexual contact between this person and this person. This person is infected here. But this person otherwise stays in a household with a certain number of contacts. This person otherwise stays in a household with a certain number of contacts. If you allow this person here to be infected here and then to transfer that infection to other people in the household, what happens to the way mpox moves between people? So again, you use an SCIR model to label the different states. You do a lot of work in trying to figure out what is the numbers that should actually enter here in terms of how long, how efficient is it to transmit, how long do you stay in each of these compartments, etc. You construct networks that are these combination networks of both the MSM as well as people they interact with, the family members they interact with here, based on the data available, the limited data available on these networks, and then you put these together. So there's a lot of information here. I mean, this is different rates at which you transfer from two household members here. These are different rates of transfer of infection within the MSM network. That's the betas here. And these are different curves, all infected men who have sex with men, infected non-MSMs. So what you should note here is that these dark lines here are the MSM network. So they peak and they come down here. The blue colored ones that seem to last much longer are the ones that come from their family members. So this, what's happening is the following, that this disease spreads very fast within sexual networks, MSM networks, but somewhat slower between the family. So it goes to the family, goes to a workplace, comes back to the family, etc., etc., etc. That gives you this long tail that stretches out. So when you think about these, the moment you have transmission possible to family members, you say that instead of, if you're looking only at the MSM network, you will see a peak and something come down. But you'll be ignoring this long tail that exists, that can last 300, 400 days over here, that comes from the non-MSM part that sort of creeps gradually through the whole network here. So it's this movement of infection between the MSM and non-MSM that lead to complex structure, at least 2 time scales. And you can sustain disease spread in the general population through the spread within the MSM sexual network and get this long tail of involving even weak spread. And you have to know this if you want to be able to control it. You have to be able to address the population that you do not think normally should have been addressed, because you would normally have been looking at the fast spread within the MSM population. But now you realize you must look beyond that. So this is BharatSim, as I said. You have behaviors and interventions, lockdowns, vaccinations, changes in behavior, social contacts, etc. It relies very much on the synthetic population. It puts in, you can choose your own disease dynamics. This is constructed as a framework, so it's not, you can put in whatever type of disease structure that you actually want, and it produces output in the form of curves that look like that, and you can see how they vary. Okay, so what next for BharatSim? I told you I'm interested in a whole bunch of problems that we're currently doing with this. But over 2 to 3 years, I want to rewrite it, maybe in Julia or something, to be faster, more efficient, retaining its outward look and other functionalities. Very core to this is the synthetic population. And I think this almost deserves a separate effect on its own. How do you construct good synthetic populations for Bangalore or Pune or Delhi or something like that, so that you can ask all of these questions of that synthetic population? This is an extremely important question, because getting private data from individuals has a whole level of complexities, and you need ethics of human research ethics boards, you need IRBs, etc., to allow you to collect information that potentially is sensitive on the population that you have. On the other hand, if questions of disease, if you can address them by having really credible synthetic populations which are benchmarked and you know how they're actually behaving, you can ask many of these questions in the beginning on those synthetic populations, and then try and understand, can additional information about that population be brought into play. We're interested in environmental variables, temperature, humidity, etc., looking for non-communicable diseases. For example, heat stress in a population. How many? It's already 30 to 36 degrees in Bangalore. It will probably cross 40 in a couple of days. Delhi's at 43. This question of heating in our cities is a very important one. What are the consequences for deaths that come from that is something that everyone is very worried about. And One Health in general. How do you look at the intersection of human, animal, and environmental health together? We are interested in vector-borne diseases. This is again water bodies within the greater Bangalore area. There are seasonality effects here. There's hydrology, it flows inside this, and mosquito habitats in regions where water is stagnant. One area we're interested in is non-communicable diseases. And so if you imagine these are people here, these are each is an individual. This is a lifetime. This person is born here and dies here, born here and dies here, etc. What the synthetic population does is to give you a cut in this particular, it's a cross-sectional measurement over here. Now, if you had enough information about risk factors, what are called epidemiological risk factors, diet, family history, air pollution, smoking, alcohol consumption, etc., 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 you can say that this, I have collected this on the population, but I can now try and apply it to my cross-sectional data that I have here. So here's my individual here. At this point, given a certain combination of where they're staying, what food they're eating, what socioeconomic class they are, they become pre-diabetic at this point, and a little later they go into full-blown diabetes at that particular point. So it's as though I have taken my synthetic population and made it my large sort of study where I put in all the information that I have about everything that predisposes you to certain diseases, metabolic conditions or respiratory conditions, etc. And this in turn will affect life expectancy and the nature of demography. So these are questions that one could answer in principle with a good synthetic population. So what you're doing is predicting the forward histories of agents, the likelihood of non-communicable diseases, but also what interventions you can take. If you can change the pollution that someone is subject to or change their diet in some way, can you alter the point at which they might develop this disease at a later point? And again, good synthetic populations, good mapping of risks at the epidemiological level will enable you to do that. In the future, we want to integrate all of these things, these determinants of health into models and design potentially better health systems. And again, the reason for doing this in my TB example is a nice quote from here. TB is a social disease. Its understanding demands that the impact of social and economic factors on the individual be considered as much as the mechanisms by which tubercle bacilli cause damage to the human body. We've understood that there is a social component to many diseases. The challenge right now for new models of disease is to put these components in, because we don't understand them well enough. And potentially the way of looking at agents where agent properties themselves can vary from agent to agent is a nice way to do this. Okay, so that's all I had. This is BharatSim itself has been sort of funded by various people here. Currently by the Emphasis F1 Foundation, some work by the NDMC on the typhoid, work at Ashoka and the Lancet Commission. All of these are important, and certainly these are all the people who are involved in it, but I just want to single out Philip Cherin as a PhD student who is now in Denmark, as a person who really put his heart and soul into thinking about this particular problem. So that's all I wanted to say. I wanted to give you a broad survey of how one thinks about disease models in this day and age. But more than that, what are the larger questions? I mean, this could have been one talk about just one of these things, like the H5N1 talk, etc. But I wanted to give you a bigger picture of the question that we don't know the answers to yet. We do not know how to integrate social and economic information into the social determinants of disease. That's going to be important for thinking about non-communicable diseases. It's going to be important to thinking about tuberculosis. That was the example that I used. And the underlying idea here is that models are important because they're the only way to be able to develop policy in time. Much policy is just because a bunch of experts typically doctors sit and say, look, I think this is going to happen, I think that's going to happen. But overall, the world is moving towards a situation where there's much more quantitative input that is required, and every country does this, and slowly we are also beginning to do this. So getting the tools in place to understand this, what's going to happen in India in the future with all of these, any number of terrible public health problems that we might have, is important, and this is one way of beginning to think about that. Thank you.
Thank you very much, Professor, for delivering an interesting talk. Are there any questions from audience?
So, how these agent-based model help us to develop early warning systems?
It doesn't really. I mean, you could ask, that's a more complicated question. If you asked about Nipah, for example.
I think he has. Might want to repeat the question.
No, he has a mic.
He has a mic.
No, for Nipah, for example, you might want to ask what is the overlap of a person with a bat, with a fruit bat in this thing, or with infected fruit. That falls in the class of what are called One Health questions, because they're human, environment, animal interfaces. One could model, but there's not much use modeling because we don't know enough about that disease ecology to be able to put it into sensible models. So it might be better to, that is a question that is probably more properly a disease epidemiology question and less of a modeling question. Because to figure out where your next hotspot is going to be is not so easy. And that really relies on data collection. And what you do need is sentinel surveillance that actually goes, samples bats, looks at possibilities that this might infect humans, etc. And even those the tools for deciding that are not really there.
I just had a technical question. So does BharatSim allow you to download synthetic population for an event structure? So say for example, I just want age and maybe how they are structured at homes and schools for a more custom modeling approach. Is that something which can be generated for a particular dimension of people or various different factors?
BharatSim doesn't allow you to generate that data as of now, but that certainly would be a nice way of doing it. We're planning to put that in. Right now I have no programmers to sort of help me do that. But that would be nice to sort of, and one way of doing it would be try and see, can you use these new AI ML methods in doing that, where you just specify the structure of the population that you might want and use these tools to generate a population. We haven't tried that, but that's a possibility. Training it on BharatSim-like data or actual social surveys, and then getting it to generate data of the form and type that you might actually want.
How do you parameterize these models? Is it medically parameterized, or do you look at the time series you generate and compare them with what's observed?
Well, parameter choices are largely medically and clinically obtained, and they're often the hardest to do because you have large ranges in which you can be confident that the value falls in that, but it's hard often to shrink that to something that's more reasonable. So one way to do it would actually be to look at your predicted course of cases and compare that to the actual numbers of cases. But often that's not very good even then, because people, if there are asymptomatic cases, you may not pick them up in standard surveys. People not going to be tested is another situation in which you will not, they're staying at home, in which you will not pick up the real numbers. So all of our COVID work, we had to introduce a multiplicative factor between the actual observed number of cases and the true number of cases to be able to compare. The only way you can do it is retrospectively, because if you can do serological surveys, you can figure out how many people have been infected. In fact, that was a big surprise when these surveys were actually done, because several states in India claimed very small numbers of cases, but actually they were at 80 to 85% infections when you actually looked at this. So those are good ways, but they can only come later, in which you go back and then, by then, your disease has gone up and come down. So it's a tricky business, and deciding those multipliers isn't easy. That's again where the skill of the epidemiologist comes into play.
Hi, can I? So this is question about policy. There is a time scale for doing research and publication, right? And how does that go along with the policy, influencing policy and having the decision makers act on it? What are the challenges as well as,
What are the scientific compromises?
and also, what are the sort of, your experience in being able to sort of, get this done? It's very, very, I find it incredibly hard and unimaginable.
As Rajesh knows, you also know, this is very hard. And you have to make a choice often that you will not be able to publish, except much later when no one cares about what you publish, in the heat of the moment when influence. But that's a legitimate choice of say that, look, I'm interested in public health of my fellow Indians, and I will give that priority, and my own publication record, I'm not care so much. That's an individual choice. And compromises, there are of course lots of compromises that you have to make in order to be effective in getting things done. But if that's, every individual has to figure that out, where they draw the line. And I prefer to be able to comment from the outside, because I like that distance, but rather than be all out together with government and not in a position to make any outward statement, because I think also public communication is also very important. But in order to do that, I have to give up other things. So as I said, it's an individual decision that everyone takes on their own, decide where they're comfortable drawing the line.
So in terms of the non-communicable diseases such as cancer, for instance, what kind of predictions from these models can help inform policy? Because cancer, unlike many other diseases, it takes many years to develop, depending on the cancer we are talking about. And the time scale of simulations, for example, in the epidemics is say a month or an year, but here we are talking, so it's much smaller than the typical lifetime of an individual. But because you gave the example of pre-diabetes to diabetes, I'm just trying to extend it
Yeah.
to think about other chronic diseases which are going to have a huge impact on our public health burden.
That's a great question. For cancers, I don't know what the answer is. I mean, if you have the sort of information that came out of the rations trial about nutritional supplementation, you can say that, look, here I have my model population, here is whatever 60 million people in this particular Indian state. I know what their base level of nutrition is. And then I can ask, if I provide this at this particular cost to this particular section of society below the poverty line, what may I expect in terms of public health outcomes 5, 10 years down the line? That's something that I can do because the base population is very, there are people who are 2 years old, 5 years old, 10 years old, 15 years old, some have pre-existing conditions already. If I'm able to take that statistical information and put it in at the individual level, then I can project forward 20, 30 years down the line, and I say the actions that you take now will have an effect. You may not see it the next year, you will see it 10 years down the line, 20 years down in terms of what your society will look like. That I think is a powerful statement if you're able to say that. Cancer, I haven't thought enough about what the analog might be. I can see it clearly in the case of TB, and I can see it in diabetes too, because estimating burden is a big part of what the ICMR does and all public health. What is the current burden of disease? What is going to be the burden 10 years down the line? How is that going to change? And what can we do to intervene? So if you have an idea of effective interventions, and you have a base population which you understand well, you can really be very granular about where you can intervene for maximum effect. That would be my.
The National Cancer Institute in the USA has models for cervical cancer, which are sort of 80-year horizon, and they take into account populations, behaviors, then what are the factors for risk and so on, and then they try out various elimination strategies across years and also various intervention policies. Particularly, for example, I mentioned cervical cancer, but if you take oral cancer, you identify someone with, let's say, some lesion. There is a 17-year time cycle for progression to a pre-cancer stage to then later stages of cancer. So for those individuals, maybe you look at them for maybe 2 or 3 cycles, 6-month cycle, and then you can say you can come back after 5 years. This sort of takes into account what kind of load policies might place on the system, as well as what is needed, and then the simulations guide such interventions and propose such policies, and also look at how effective they are.
Yeah. Although we just sort of make one point, those are really individual models. I mean, said they're based on studies of individuals. Here we want to ask what are the population level impacts of that, and how do population level interventions, especially social interventions, how they might make a difference. So what we want to do with BharatSim is a little different from that, although it borrows from that same idea.
Bring in the network in some
That's right,
sense. Yeah, I had another question which is maybe somewhat related to what was a question here. Somehow if you probably bring in surveillance and bring aspects of surveillance into your simulator, look at the data and then update the simulator based on data that has been gathered, maybe that might give you some aspect of at least intervention in terms of isolation and so on. Is there some integration of the surveillance with the models that's being planned as part of BharatSim activity?
That's an interesting
Wastewater
question.
surveillance.
That's an interesting question. We thought of something a little like that, which is when we did Pune in the sequence of cases in Pune, I didn't show you that picture, but you have a spatial map of where the cases are as a function of time. Now they just start from some random initial configuration, a couple of people infected. You can either infect a whole ward, you can infect a set of families in the ward. We looked at what happens in both of these cases. But if you can relate that to the number of cases that are reported 5 days, 10 days, 15 days, 20 days down the line, you imagine simulating large numbers of alternatives. You pick only those simulations that correspond to that number at that time. You prune it, and then you run only those, and then you prune it again, you run only those. So that's where the surveillance information will become important in restricting the options that you might actually have. So we haven't done that. It's just it's something in one's head that one should be able to do it. Be able to leverage surveillance information added to this.
Thank you once again, Professor, for accepting our invitation and delivering such an insightful talk. And thank you, audience, for asking wonderful questions. If you want to connect with the speaker, please do so along with the refreshments at the coffee hut. Thank you all for attending and have a great evening.
Thanks to all of you again.